organize the convection and get some really intense rainfall rates. And that's what we're showing over here. The hourly amounts are shown, and then the accumulated rainfall over here. Um, okay, and so we have this radar-based system, NEXRAD-based system in the US called MRMS, or Multi-Radar Multi-Sensor System. And this is showing kind of the validation of how this performed during the event. The star, again, is right where Camp Mystic is located. And then this is the circles correspond to where we have rain gauges. And then the coloring, I'm so used to looking at these plots, I need to describe them a little bit. But the larger the radius of the circle indicates how much rainfall occurred at that. And then the shading of the color on the circle indicates the bias. So if it's getting redder, like you can see right here, this indicated it's a little bit drier. MRMS is underestimating here. The blue ones means MRMS is overestimating, and the really small amounts here. Um, and then we have two different versions of MRMS. This is what was running on the machines at the National Weather Service. The operational version was 12.29. We had upgraded our local machines, which is a virtually identical hardware that's running at the Weather Service. So this is 12.3. And basically, what we do is we onboard the software on our local systems, and then the Weather Service, it may take them some time before they can get a version upgrade where they do a lot of things. They may update security on the systems, a new OS, and so on. So, nevertheless, this was upgraded later that month, but I think it's worthwhile to show them both because this one was running on in real time as well. And so what you see with the older version, there's a little bit of this overestimation at the lower ends and then a little bit of underestimation at the high end, you can see. And then it's pretty hard to do this with an algorithm, but it actually fixed both of those. So it kind of reduced the overestimation, improved the underestimation. And so if you look at the stats, they're really solid. 12.3 with this version because the bias is it's basically unbiased, very high correlation coefficient. And so basically our takeaway, at least for this event, I'm not going to say this for everywhere all the time, but the errors in the radar-based rainfall estimates are similar to maybe even smaller than what you get from the rain gauge observations themselves, because the rain gauges are going to have errors due to undercatch and representativeness and wind and things like that. But this is about as good as we can expect with radar. And so next, what we do is we have the system in the US called Flash, and it has several products that are generated from that, one of which is output from a distributed hydrologic model. And typically, what forecasters use as System 4 is they're looking at the gridded outputs. So, not so much the hydrographs, but they're looking at the gridded outputs, like I'm showing on the upper right. And that's showing the stream flow. And another product they use a lot, we call the unit stream flow, where you take the stream flow and normalize it by the upstream basin area. And that's kind of the primary tool that they're using for issuing flash flood warnings in the US. It's been in operations in the Weather Service for a decade now. And this shows how the model performed in real time during this event. And so the black dots, I'm showing you on the North Fork Guadalupe and then directly downstream where the South Fork comes in. And then the black dots are showing the observations, and then here you see the black dots, and then I switch them over to X's, and that's because the gauge was lost. And then the X's correspond to when they estimated the stream flow based on the post survey. Um, and what you can see, I put the traces from the different QPE inputs that were put into our flash system. So the gray was the older one, and then the 12.3 is the newer version. And you can see it worked pretty well for this event. You know, we were only off by a little bit of underestimation on the peak at the very top end, and very good on the timing. Um, and so the thing that's maybe the surprising about this is this model doesn't get calibrated. The parameters are based on a priori parameters. So it hasn't been tuned in any way. And this is how it runs out of the box, like basically everywhere in the US. No data assimilation, and this is what was produced in real time. So it worked pretty well for this event. The one major caveat with this is that it's purely diagnostic, meaning that it's getting rainfall rates in real time from the radar. And then we run this model every 10 minutes across the US. And so the only kind of lead time that you're getting is basically your basin response time, right? And that could be 15 minutes, could be a few hours, but that's the main limiting factor is that we're dependent on observed rainfall. So that kind of limits what you can do with the predictability of this event. And then I put this slide in here because I want to get us a little bit comfortable with this basin. So this is, again is the Guadalupe River Basin. These are monitoring stations. So this is on the capturing rainfall from or stream flow from the entire basin, and then there's another gauge on the North Fork. But if you look at the precipitation in the background, you see a couple things that are interesting. First of all, it's concentrated really on the South Fork, and no gauges here. But with the distributed hydrologic model, we can put monitoring points anywhere we want. And so we're going to put one on the South Fork, and there's this little other creek that comes in. It's tiny, 25 square kilometer catchment called Cypress Creek. And if I zoom in here, you can see what it's doing. It kind of meanders in from the south. And then this is where the camp is. So it's right at the confluence of this tiny little creek that, people swim in and everything. And then this larger South Fork, which again is usually pretty calm. I've floated it myself, and you can inner tube down it and everything. It's usually pretty calm. Okay, and then the other thing I wanted to note about this, if you look at this rainfall footprint, if you these little boxes in here are 1 kilometer boxes. So if I took this rainfall footprint and shifted it to the south, let's say by 10 kilometers, then I basically would have cut this event, in half or maybe in thirds because you go to these other basins down here. So it's pretty strange that this rainfall remained almost entirely concentrated within the Guadalupe River Basin, and that really exacerbated some of the impacts of the rainfall and the stream flow. Um, so now what we're going to try to get into is the predictability of this event, perhaps better using some numerical weather prediction tools. So at NSSL, we have something called the Warnham Forecast System. And in this particular case, we ran it at 1 kilometer version. So that's a grid cell spacing. It's actually very similar to radar data when you run it down to this scale. And so it is a targeted domain. So you can't run this over the whole US. It's too computationally expensive. So it's a 750 by 750 kilometer domain. And then we run it every 30 minutes is when we initialize forecasts. And then they provide you a forecast up to 6 hours in the future. And you get 18 different members, and then we get precipitation outputs every 5 minutes. So we're getting down to the scale pretty close to our observed radar data. In fact, I even tricked the model when I put this in here, just with the file names. It actually thinks it's radar data, but it's actually a forecast of the precipitation. Um, and then I'm not going to spend a ton of time on this. This is just comparing the QPEs directly to the quantitative precipitation forecast. And so the other operational system in the US is the HRRR high resolution rapid refresh model that runs operationally over the CONUS. And basically the point here is that it did have a signal early on in the event right there, that's 0Z. And then it loses a signal, whereas the Warnham forecast system over here, this is an ensemble output. So I'm showing the 50th percentile. And then it's a little bit too far south early on, and then it catches up in here and does quite a bit better as time goes on. And so the next thing that we're going to do is we're going to give the hydrologic model the analyzed rainfall for the prior times up to t=0. And then from here in the future, when we run the model, we're going to give it the ensemble QPFs. So 18 different members are going in. And then we can examine the hydrographs from this. And I put in just a couple pictures of the CREST model for those who aren't familiar with it. This is what we use. It's fairly simple. It's not I would say this is a very standard kind of hydrologic model setup, and we depend on the VIC kind of concept for generating runoff or variable infiltration curve. What's perhaps unique about it is all of the parameters that we have in the model are not tuned based on stream flow observations and turning knobs and optimization things like most do, but we tie it to just these a priori parameters that are based on observable features of the Earth. So here's a national land cover database from NASA that we get that tells us something about the imperviousness of the land surface. So you can see, where cities are located here and there, and those are obviously a lot more impervious. So the model knows about that. The rest of them are derived from like soil permeability, texture maps, soil depth maps, and so forth and so on. So that's how the models run. And that way, if we get a certain behavior at a given gauge location, we can expect that similar kind of behavior at ungauged locations. Okay, so now we're going to start with the HER, or the high resolution rapid refresh. And then this vertical gray line that's moving from left to right is showing different forecast initializations. So early on is 0Z, which is 7 p.m. local. And you can see there was some indication. You can see some of the higher stream flow amounts that we got early on, and then it kind of loses it here, which is strange. And then it finally comes back, but I don't give it much credit whenever we're, past 6, 7 UTC, because now it's getting observed rainfall that's going into the simulation. So it kind of by definition should do that, should converge to that black curve eventually. Um, so that's the HER. And then if we look at the Warnham forecast system on this slide, and also I wanted to establish that we ended up using a moderate flood stage as kind of a threshold for saying like, okay, we exceeded something bad, and then we can start counting, how many members exceeded the moderate flood stage. So I'll give it just a second to build the loop. I'm kind of getting some slowness here on my computer. I'm sure you are as well. Um, but the basic point here, and I was afraid it would do this, and I think I overlaid a 2Z run. There it is. No. Yeah, okay. So here's the 2Z run. And the reason why, so this is at 9 p.m. local. And there were a lot of stories that came out about this event, like a lot of the local emergency responders and so on, and emergency managers, they went to bed, around this time, 9 or 10 o'clock. And it was on their mind like, oh, yeah, there's going to be some rain, but we've been in drought. It's middle of summer. It'd be kind of welcome. It wasn't really, nothing had struck them that this could potentially be a big disaster. But what I'm showing here, this is at 9 p.m. And then we have quite a few members that have exceeded the moderate flood stage. So it's giving a decent indication, this many hours in advance of the event, that there's the potential that something really bad is going to happen. And so this is showing the basin outlet, 746 square kilometer catchment. So that kind of gives you an indication about how big your target is. Now what we're going to do is we're going to zoom in to right to Cypress Creek, this tiny little catchment, 25 square kilometers. Um, while I talk here, I'm going to let the animation build, hopefully. I tried to close out a bunch of files earlier, hoping that would fix this, but it's still struggling. So you can see where the threshold discharge that I have on there. And then with time, as that little vertical gray bar moves from left to right, then you'll start seeing more and more members that are exceeding that threshold discharge. And then another thing that's interesting about this, if you look at the basin average precipitation plotted on the secondary y-axis inverted here, you get some incredible amounts for basin average rainfall, 120 130 millimeters on basin average is pretty impressive amount. And so I think I do the same thing here where I'm going to stop it at about 2Z, since that animation's clunky. Um, see if it's going to do that. There it is. Okay, so here again is at 9 p.m. local. So most people on a Friday night, most people haven't gone to bed yet. And look at how many members are exceeding the threshold discharge. You're getting at least half of them here. So even on this tiny little target, 25 square kilometers, so you're only getting like, a 5 by 5 grid cells that are contributing to this thing. And yet you've got half of the members that are indicating that we're going to go over threshold discharge and become at least a moderate flow event, moderate flood event. Um, and so one thing I wanted to show here was this warn on forecast, the probability of updraft helicity. So this is showing you basically how much spin you're getting in the updraft portions of the thunderstorm. And this is Guadalupe River Basin and Camp Mystic. And you can see with the 60 run that it's got a very high probability of exceeding this threshold amount, meaning that the model's picking up on this rotating supercell in the basin. So that's the reason why it's basically getting it right. It's getting it right for the right reasons. It had a supercell in there and it produced this copious amounts of rainfall. Um, and so we did this exercise for four different, for the biggest catchment, and then on the North Fork, the South Fork, and then this tiny Cypress Creek. And this is a chiclet plot. And if you're not familiar with it, it's basically a time series from left to right. And these are different forecast initializations. And then what we did is we counted the number of times a given member exceeded the threshold discharge, which was a moderate flood stage for each of these. And so I'd like to draw your attention to the 2Z02 UTC run, which is 9 p.m. local. And that's where you get this big jump. That seems to be where the model really caught on. So you only had, two, three, five members that are exceeding threshold. And then all of a sudden at 2Z, you're getting well over half of them. And then they stayed up that way for the most part. You get a little bit of a dip here around 5Z, but you get it, showing red most of the way, and then they're all exceeding it, around 6 UTC. This shows you when the flash flood warning was issued in terms of timeliness. Uh, Hang on just a second. I've got some people coming up to the house. Hey, Steph. Damn it, she's on a phone call too. Okay, let me just finish this out. Um, and then the basin, sorry, the vertical white lines are showing you whenever the the peaks were established at each of the stations. So I'm just going to leave this slide up here and let you read it, and then I think I'll stop there because I'm probably well over time. And for those that want to read this, both of these papers are companion papers, and they're both out on early online release with the Bulletin of the American Meteorological Society. So I'll just stop there. Thanks.
Great. Thank you, JJ. Wonderful. Wonderful. Yeah, that flood was one of the deadliest. I mean, I think it is around like 130 people killed by this flooding, right?
Yeah, it was the deadliest since Big Thompson Canyon, which was
Yeah.
1976, and that was there. I think there was I think Russ Schumacher was telling me about it. Maybe this summer they did some sort of a symposium, like the 50th anniversary of Big Thompson.
uh, yeah. I mean, that type of flash. And then I am not sure why decision makers and the stakeholder, they just thought that it is going to be moderate kind of flooding, it's just can be during particularly nighttime. Yeah.
Yeah, that was the yeah, and there was a lot of just misinformation that came out about it. I think some people, at least in the media, I saw a little bit of folks attributing it to like just an act of God. Like this is we'll never see it again. This was so insane. How can we prepare for this kind of rare event. But the fact of the matter is, there was an event that was very similar in magnitude in 1932 that was captured by the gauges there. In fact, there was this event didn't exceed that on the North Fork. So it wasn't even a record on the North Fork. And that
Yeah.
was in 1932. And the camp had been established in 1932, and there were people there and no radar, no warning system, no models back in 1932, and only a few people died. But the difference was it happened during the day. So
Yeah.
that's a pretty big factor.
Yeah. And then they issue warning sometimes in the morning, right? Early in the morning. 6:30 that you show on one of
Yeah.
your I read?
Yeah, I do have that timeline on there somewhere. Yeah, so the flash
Mhm.
flood warning was issued at around 6:15 UTC, something like that. So,
Yeah.
you know,
Wow.
it was well in advance. The warning was not problematic at all. I mean, you can see the distance between the purple and the white line is how much lead time you got on that warning. That's
Yeah.
whenever the moderate flood stage was exceeded at each of those catchments.
Great. Yeah. Any question? Anyone? Oh, Josh, how are you?
Hey, good. Yeah, sorry I was a bit late this morning, but
Yeah.
yeah, JJ, that was a great presentation. I thought it was really interesting. I'm really curious about the I don't know what you call the WOFS flash system, right?
Yeah,
So
yeah.
you're running this at like 1 kilometer, but this was like very isolated to like evaluate this event, and you talked about how it's not feasible to run this the scale, but it seemed to make a pretty big difference to be able to run. And I'm not sure if the her system runs ensembles or not. It didn't look like it. So
Right.
I'm
No, I
wondering.
think yeah, the her there's a her E. I'm not an expert on that. I would need to ask somebody at GSL, but I think they do more like some time lag ensembles and things with the her. Um, so yeah, that's probably the biggest limitation with Warn Forecast is that it's a regional domain that's basically selected daily. So
Okay.
forecasters kind of choose. It's usually going to be based on depending on what the experiment is. It's going to be where SPC is going to have a moderate risk or whatever, and then if it's rainfall oriented experiment, then we'll be looking at WPC outlooks on heavy rainfall potential and things like that. And then the forecasters will make a decision where it's going to go. So that's kind of where we're going with this. It's our intention. So we did get some project funding for this, and so we're hiring folks. I think I'm going to get as many as 5 employees. So if you guys two postdocs and a couple GRAs that should come out any day, really now on the advertisements, and so within a couple of years, we're going to have this running in real time, and so we'll be able to have Flash running anywhere that regionalized domain goes, and then it'll be basically adding flash flood products to the Warning Forecast system because they have a number of severe weather products already. There's tabs on there that basically for lightning and hail and wind and tornado rotation, all that stuff's already there. So this will kind of round out in terms of add another severe weather phenomenon to it.
Yeah, I mean, it seems like it has the potential to give a lot more lead time for some of these things. And I was curious about what your intuition is on this relative to like how much of it is due to the higher spatial resolution versus how much is due to having the ensemble aspect. And
Yeah.
then what, if any, do you think the boundary conditions are playing a role into that? And where do you get the boundary conditions for these forecasts?
Yeah, all good questions. Where do I begin? So on let me just start with the resolution going. Nominally it runs every day now in the Weather Service, the Warning Forecast, but the 3 kilometer version.
Okay.
And so we reran this experimentally, the 1 kilometer version. And what we found, there have been a number of studies that have shown that the 1 kilometer version does a lot better with like mesoscale circulations and storm scale things. It does a lot better job at capturing that. And it's not just the 1 kilometer grid that's resolving it. And I think what the main reason what's happening inside is that it's a very aggressive data assimilation scheme. Like a lot of the DA approaches are just kind of like nudging latent heat profiles and things like that, and just adjust the temperature field, and that's basically it. And then everything else is going to kind of adapt around that. In this case, they're actually assimilating like radial velocity, and and the microphysics and so on are being impacted by that. So they're actually getting different the cloud. species and different things like that are all being assimilated into that. So it's a much more ambitious DA than you typically would see in NWP. And I think that's probably, and it's more effective, by the way, at 1 kilometer with the radar DA than at 3 kilometers. So I think that's probably the biggest impact with the 1 kilometer wasps in the frequent cycling too. That's the other thing is that I see that with the her all the time. It's running hourly. And it happens all the time in our neck of the woods where a storm pops up and the models didn't know about it, and pretty much your forecast thereafter are kind of blown, because now you got outflow and the whole environment's disrupted at that point. But in the case of warning forecasts, it's actually doing a DA every 15 minutes. So if you get that surprise thunderstorm that pops up out there, it's assimilating radar data. So it's going to see it and say, oh, I've got echo, I've got velocity, I've got winds, everything is going to be thrown into the model and it's going to quickly adapt and catch on to that. So it kind of has that luxury of being a little more agnostic of where things are changing quickly. So and then the last question was boundary conditions and gets it from the her. And so that's sometimes you can see some boundary effects on the boundary conditions where there's some studies on that, but I'm not an expert, so I'm not going to try to speak to it too much. But it's like an edge effects and things like that happen.
Cool. Yeah, so okay, last question. You might have mentioned this, but I forgot. How are you doing the ensembles for the WOFS?
Yes, so the ensembles are created. There are some IC and BC perturbations on the initial conditions, and then the other two there's land surface parameters or land surface scheme is adjusted, and then the other one. See, it doesn't even have parameterized convection, so it's explicit microphysics on the convection. It's a CAM. And there's I think it's a radiation. It's something you wouldn't expect. It's
Okay,
I
so
think
it's
it's
like
I think it's land surface and radiation schemes are the two that are nudged, that are
a
physically based, and the other ones are just ICBC perturbations.
okay. Cool. That's really interesting. I think, yeah, it seems really promising, like a great way forward. So really cool work. Thanks for sharing it.
Yeah.
Thank you. Appreciate it. Thanks for
Thank
the
you, Josh.
comments. Trying to see
Great,
if I
great,
might
great.
have those boundary condition those details are probably in here, but I can't scroll through this very fast. Sorry.
You're
There we
good.
go. Yeah. Yeah, I don't say it, just say 36 members, 18 forecasts. So that's it.
Yeah.
Nice. Any other question you guys may have?
Yes, I have a question.
Yes,
Uh,
Nima.
thank, Thank you so much for your exciting presentation. Actually, I don't know that you discussed about it or not, but even the computational cost of running this model across the Konos, how can it be operationally applied to similar future extreme events? I mean that because you use it for past event and try to use this model. I just wonder about the future events here.
Yeah, good question. As I mentioned, this has been funded through Precipitation Prediction Grand Challenge effort within NOAA. So within 2 years, that's what we expect to be doing is running in real time and for future events. So the trick will be there is to get your domain in the right spot. So if you get surprised by something you didn't anticipate, then there's not much we can do about that. But in terms of speed up, have been some efforts. Warn and Forecast System, they have a paper out in GRL where they use the Google GraphCast system and basically adapted that for Warn and Forecast. So they have an emulator called WASPcast. So that's one way at which we can speed things up dramatically by a factor of 30 or so. And so that enables things like maybe a bigger domain, maybe more frequent runs, more ensemble members, and so on. And then likewise, we're doing the same thing with the hydrologic model. We have an emulator that we developed for that, and that's presently in review. And so that's another, and we also got a speed up of a factor of 30, where you basically just emulate what the model can do. And it was shocking to me how well those emulators can work because there are certain instances where they showed me on the Warn on Forecast system with WASPcast, it actually did better than the physics-based system on certain events where I'd learned something. I don't quite get it all, but it's all pretty shocking to me. So that's probably the future, getting things to speed up.
Yeah, using the emulator by machine learning techniques is a
Yeah.
kind of to speed up these kind of models in case of computational. Yeah, it's your presentation was so cool to me. Yeah, thank you so much. Yeah.
Great.
Thank you.
Any other
Appreciate that.
question? So JJ, you're very bright. You developed EF5 years ago. I remember I ran that on that time. So what is the difference between this WOFS and EF5? Are they the same? I know EF5 does assemble forecasting, it has routing kind of a scheme and all. Uh,
Yes. Yeah, so EF5 is what I was showing here. I mean, that's CREST model is contained within EF5.
okay,
And so that's an ensemble system for flash flood prediction. It's hydrologic. And then Warn on Forecast system is numerical weather prediction system. So
okay.
so we're finally kind of marrying the two. So these developments were done kind of in parallel for a
Yeah,
long time, and it took a while for Warn on Forecast system to mature basically, but we're pretty close now. So that's why we decided to go ahead and start exploring whether we could do this coupling. And this was our first time to couple the 1 kilometer Warner forecast with flash, and then we got these results. We're like, whoa! But of course, this is I always tell people around me like this is the honeymoon phase. This is like everybody's happy, and we haven't gone through the first argument yet, or the
yeah. Oh,
So,
yeah,
but we're definitely in the honeymoon phase. And but that being said, we have tested the coupled system on a couple monsoon events in the Southwest, and it works pretty well for those too. So I'm hopeful. But there are going to be some false alarms and things
yeah.
like that, without a doubt.
Great, great. Have you contacted the Southeast River Forecast people? I think they should be, interested in this. And uh,
Yeah, not yet. I usually start doing more outreach like that when our operational posture is improved a little bit, because now this is going to be just purely R&D for at
yeah,
least a year and a half, and then we'll start kind of communicating if we can start standing something up. And forecasters get really engaged when you have something to show them in real time, even if it's
yeah,
your own web page or something, and you'd be like,
yeah,
"Hey, go look here." And we'd appreciate, or bring him into Norman where we have a test bed experiments that we run in the spring.
yeah,
That's another way. That's something we'll certainly do once we can stand up the system and start getting forecaster feedbacks, and then they start spreading the word and getting excited. So that's a really effective mechanism for doing that.
yeah. Great. So another avenue would be Cairo too. I mean, I don't know you know it or not. I mean, the National Water Center, they got
Hmm.
money from NOAA, 300 something, right? So those folks are doing great things as well. Um, I know they are just improving the national flood models, and some folks they're working on the river routing models of those national flood models. Um,
Right.
Perhaps those folks I mean, the main kind of group is in University of Alabama. So I think those folks should be also interested as well.
Yeah, yeah, I think they are. We had a workshop back in the spring that was joint between Cairo and then our cooperative institute at University of Oklahoma, CIRO.
Yeah,
They're almost spelled the same, but nevertheless, that was kind of the first time the two cooperative institutes have really gotten together and had a joint workshop. And then I think we organized this session for at AMS. So Josh might have seen that. Katie Van Workoven is the session organizer for that. So that's kind of an outcome from the workshop. So
yeah,
yeah.
great. Very cool. Nice. Any other question you guys may have? Thank you very much, JJ, for your great presentation. Thank you. Thank you.
Thank you. Appreciate your
Thank you.
attention.
Yes.
Good
Wonderful.
questions.
So, a couple of announcements for those of you who are new here. So we are actually starting working on or crosscut report that include. We are trying to include the research outcome across the globe. So if you've done any kind of research work and publication related to flooding, I encourage you to enter your citation and contribute to this report. We will start shaping it in 2027 after we finish our monthly meeting, hopefully this year. And then you will receive a copy of it through GEWEX listserv. And we encourage the community feedback on the draft before we finalize it. So please add your publications or any kind of papers, report that you have originated from your flooding research. So we would be happy to include it here. And our next speaker is Dr. Tang from Department of Earth System Science, Tsinghua University in China. So please mark your calendar. And here is a list of our presenter. You can find the YouTube video of the presentation on the GEWEX YouTube channel. So please check it out. And if you have any questions and if you want to get involved in this initiative, let us know and email us. And this is my email address. Let me type in. We appreciate community contribution, and this is our kind of community initiative, and we are coordinating this initiative here with Dr. Rondi. And also Dr. Bosco from University of Sydney, so he won't be able to join due to the time gap. And I appreciate your participation. And again, thank you very much, JJ, for being here today. Thank you for the great questions. Thank you very much. We see you
Thank you.
in our next meeting next month. Thank you.
Thanks.
Thank you very much.
Yeah.